In astronomy, these moments are regularly used to characterize a spectral line, for example. This is an example of an actual spectral line. So this is carbon monoxide, a rotational transition with rotational quantum number changing from 4 to 3 in DR21, which is a star-forming region in Cygnus, so somewhere on the northern sky. What's plotted here is on the x-axis the frequency in units of Doppler velocity. So that's common that in astronomy you give frequencies or spectra on the frequency on the velocity scale, because it relates the measurements to kinematics, to local kinematics. You know from quantum mechanics that this is a discrete energy level transition which has one frequency. So if you observe, so it should be an infinitely narrow peak. And since you have a Maxwell distribution in the gas and Doppler shifts depending on the projection of the velocity of each single particle, you get a Gaussian. That's the expectation value of the Maxwell probability distribution in three-dimensional case, gives you a Gaussian. That's how this, and this is because of microphysical velocities, and that makes velocities interesting. Also, if the source would have some systematic velocities like outflows, inflows, translation, we could, using such spectra, quantify them directly in kilometers per second. Okay? So, now, interesting statistics here are, for example, where does this peak? What's the total energy emitted by all these CO molecules? So basically, what's the area under the curve? How turbulent is the local medium that emits the radiation? Because if it's very turbulent, we get a wider line because we have higher, stronger, a wider velocity distribution, and so on. If we have an outflow, if we have most of the gas flowing in our direction, we would have observed a shift to the left-hand side, to negative velocities, and so on. Yeah. So what we see here is kinematics in the local object. And to observe this, since this is binned data, yeah, so we have some detector that's counting basically photons in some velocity or frequency velocity or frequency bins. This is a binned data that we get, and we compute, for example, the zeroth moment, which is the integral over the distribution, or in this case the integral over the data, just like this. dV here is the width of a velocity channel, assuming it's a constant, and I is the intensity at the eth point. So here, and adding them up, multiplying them with dV gives us the integral. And assuming that we did some data reduction, making sure that the noise level is here on average 0, what we get is the area of the signal. Yeah. The first moment is computed like this. That gives us the intensity weighted velocity of the spectral line. So what's the most common velocity? And this gives us the dispersion, the velocity dispersion, or the sigma. For this data, if I compute this, I get, first of all, I look up here the velocity difference. So that's 1.35 or 36 kilometers per second. And then I sum up all data points and multiply it with this, and that gives me integral of 82 point something Kelvin times kilometer per second. So that's the one common unit in radio astronomy. So that's the Rayleigh-Jeans temperature times the velocity. Then we can look up where's the center of the line. That's 1.6, which is here. And that's because we have here some side wing that shifts the center from here, where we would by eye find it, somewhat to the right. And the full width half maximum, or the scatter measure, is 23 kilometers per second. So that's 2 tick marks here. It's okay. Yeah. That's how you use it in the astronomical example. And the advantage is you can do this on the data. I don't need a model. What would be other possibilities to specify, like where's the peak, how wide is it, what is the area? What can you do to answer these questions? Any ideas? What would you do? You should answer, what's the total intensity observed? Integrated intensity, or where does it peak? Any ideas? That doesn't matter. Yeah.
Maybe just like first order condition. Just
what's that?
The derivative and just
Okay. Well, yes, like you learned exactly. Where's the maximum of a curve? First derivative setting to 0. Okay. Yes, possibly. Should we do this on the example? Let's do it on the example. That's an interesting case. So first of all, we need the data. Can't I get it? Data analysis. Okay. Damn it. Here. So that's the data. Let's take a look how this looks like. Ugh. Okay, so that's a list of XY values. The first number is the velocity in kilometers per second, and the second number is here the antenna temperature in Kelvin. And you see, so that's what's plotted here. Now, how do we compute the derivative? What we can do is we can do the differential quotient, okay? Differenzenquotient to approximate the derivative. So that is xn. Here. So it's defined as, let's see, delta t divided by delta v. Okay? And we can compute this, so minus t over n divided by delta v. Oops. And n is the counter of the position, so the index number of our individual measurement. Okay, I think Mathematica has a function to do this on data. Let's do it manually. So table. So spectrum E plus 1. 2, that's the actual temperature, minus E, and we can do it generally because let's assume we have a varying velocity bin width, then this would be this. Okay, so that's the differential quotient for position E. So now the problem is we have, if you look at the formula, this goes from I plus 1, from I to I plus 1. If you have 100 data points, you can only compute 99 derivatives. Okay? So this changes the dimension of our data. And we need to consider what is the respective velocity this quotient belongs to. Because it's neither I nor I plus 1. So it is basically the one in between. Like this. Okay? Is this clear to everybody? Yeah? Okay. Okay, so I should go from 1 to the size or the dimension of our data that's computed with length. So let's see part. That doesn't work because we are asking it to do 100 the full. So okay. Let's call this diff, and now we plot Kelvin pro Kilometer pro Sekunde. So that's the derivative of your data. That's actually not too bad. How would you let's compare this with how a perfect signal would look like, or the derivative of a perfect signal would look like. And let's say this is the perfect signal is a Gaussian e to the minus, what did we compute as mean value? 1.4 and a sigma of 1.6. X minus 1.4 hoch 2 dividiert durch 1.6 hoch 2 x nach x ableiten, x, 1. So what let's just look at this. Okay, that's how it looked like. And if we take the derivative, warum geht das nicht? Nicht the partial.
sounds pretty narrow.
It's just a number.
Vielleicht für die Klammer?
Nee, das wir machen es so. Zu Fuß. Yeah. This is how the derivative of the perfect signal should look like. Let's plot them both to understand what's going on. So the derivative is the inclination, the slope of your curve. So that's positive here till we reach this point. Okay, then it becomes 0, and it drops again and turns negative, and here it's then things again. Okay, so you know this from Kurvendiskussion and I don't know what. And now you could look where is the root of this function and identify this is the peak position. Okay. This is a good example. You see that here you have somehow comparable behavior. Yeah? Qualitatively. But what kills you is the noise. Because you have a gazillion of peaks here. Every single one will give you a turnover from positive to negative. So to actually numerically compute derivatives on noisy data is difficult if you want to use it. You can do this. So one way is to try to smooth your data and so on. Yeah? There are instances where you need to compute the numerical derivative. On noisy data, and then you have to figure out good ways to actually be able to find the root value on data like this. Okay? But it's a good idea. Other ideas on how to do it? I somehow hinted it when I used this. What we can do is we can try to find a model. So we could try to represent the data with some analytic function and then figure out where the peak of this analytic function is by computing the derivative, or maybe we know it because we put it in. We can integrate this function. Yeah. We could make the model, our data is Gaussian. We can try to figure out what Gaussian function fits this data the best, and then continue work on the analytic model. Okay. In this case, this would be challenging because we have this inconvenient dip in the center of the line. Yeah.
We could split it and use Poisson.
We could?
We could split it there and use Poisson distribution. On one of the ways.
We don't need Poisson distribution because we have many photons, so Poisson in its limit is again Gaussian, so that's fine. Now we could, for example, say that it's not one but two Gaussians, two peak functions close next to each other. Yes, possible. We could also say there's a third one that should explain this. Maybe there's even a fourth one to explain maybe some small and then it becomes somewhat arbitrary, because if you can add up 3 or 4 Gaussians in, this always fits your data. If you fit 3 or 4 Gaussians to your data, this always fits. Always. Yeah, there's this example by, I think, Feynman, who said that you need 5 parameters to fit an elephant. Maybe I'm doing this as the next exercise for the fitting example. Yeah, you can fit an elephant with 5 numbers, so that's anything. So basically anything. The problem is this might be the result of something that's not related to your model, because a perfect source, if it's optically thin, should emit in a Gaussian. Maybe we have some absorption that's in front of the source on the line of sight. And so you immediately encounter many problems when you would like to do a model. Many subjective choices again. So the moments are not inconvenient.